welcome back. Today we will start Lecture 9-2 on Discrete-Time Systems Design State Variable Feedback Control. The objective of today's lecture is that students should be able to use state variable feedback to design a control system, to place the closed-loop poles for a control system, or to design it to have given system characteristics. The most common used control method in modern control systems is state variable feedback. We actually examined this in the continuous time earlier in this course. It is used to place the poles of a controllable system. The basic discrete time state variable feedback system is shown in Figure 1, where the input is RFK and it goes to a pre-filter, which is sometimes used to reduce the steady state error. And then you have the difference that comes out the output, which is U of K, which feeds H, and then that goes to the summer, which creates the state variables X of K plus 1, and you delay to get X of K. And you have your C matrix and your D matrix that feed together to make Y of K. And you have the controller K that feeds back your gains, which is where we get the state variable feedback from. And those selection of that K matrix is how you design for certain system characteristics or closed loop poles. The feedback gain matrix K is used to place the closed loop poles, and the pre-filter is used to adjust the steady state error, as I stated earlier. And the state equations for Figure 1 are X of K plus 1 equals G of X of K, but now here's different than the last lecture because we have the pre-filter. So this is plus H times GPF R of K minus KX of K, which reduces to G minus HK X of K plus H GPF R of K, and the output Y of K is CX of K plus D GPF R of K minus KX of K, which simplifies to the quantity C minus DK X of K plus D GPF R of K. To find the transfer function, very similar to before, y of z over r of z, it's c times the quantity zi minus g plus hk inverse times hgpf. And for a zero steady state error, the pre-filter must be 1 over c times the identity matrix minus g plus hk inverse times h. To place the closed loop poles for the system, use the following equation to equate the denominator of the transfer function to the desired characteristic equation. So it would be the determinant of zi minus g plus hk equal to the product of z minus each of the poles, and then you equate coefficients to get k. In class activity 1, design the following system to place the closed loop poles at negative 0.1 and negative 0.2. G is equal to 0.1, 0.2, 0, 0.2, and H is equal to 0, 0.1. So the first thing we're going to do is we're going to check the controllability by building the controllability matrix. C sub m is equal to H, GH, which equals 0, 0.1, and 0.1, 0.2, 0, 0.2, times 0, 0.1, which equals 0, 0.1, 0.02, 0.02. Remember, if we have a full rank matrix, then we have a controllable system. So we find the determinant of C sub m, which ends up being negative 0.002, and that's not equal to 0. So we do have a full rank controllability matrix, so the system is controllable. So now that we know we have a controllable system, you actually can find the gain vector k that will satisfy our closed loop poles negative 0.1, negative 0.2. So next I'm going to find zi minus g. Zi minus g is 0 minus 0.1, negative 0.2, 0, z minus 0.2. Then I'm going to find the determinant of zi minus g, which is 1 over z minus 0.1 times z minus 0.2 times the adjoint of that 2 by 2, which is z minus 0.2, 0.2, 0, z minus 0.1. So the characteristic equation, delta of z, is equal to z minus 0.1 times z minus 0.2, which equals z squared minus 0.3z plus 0.02. And so the original control system has poles at 0.1 and 0.2, and we're going to design the system so that the new poles are at negative 0.1 and negative 0.2. So first we need to find the characteristic equation for our state variable feedback. So we do this by finding Zi minus G plus HK. We already have Zi minus G, so this is going to be Z minus 0.1, negative 0.2, 0, Z minus 0.2, plus H, which is 0, 0.1, times K, which is K1, K2. So the result is Z minus 0.1, negative 0.2, 0.1 K1, and Z minus 0.2 plus 0.1 K2. Next, we find the determinant of the state variable feedback system. So it's the determinant of Zi minus G plus HK, and this will yield the characteristic equation. And it is Z minus 0.1 times Z minus 0.2 plus 0.1 K2 minus 0.1 K1 times negative 0.2. So when we simplify that expression, it simplifies to Z squared plus 0.1 K2 minus 0.3 Z plus the quantity 0.02 minus 0.01 K2 plus 0.02 K1. And what you should notice here is that if we replace K1 and K2 with 0, which means no state variable feedback, this actually yields the original characteristic equation for the system without any state variable feedback. So our desired characteristic equation, delta D of Z, is Z plus 0.1 times Z plus 0.2, which when you FOIL that out becomes is equal to Z squared plus 0.3Z plus 0.02. So now we equate coefficients. And what we get here is that 0.1 K2 minus 0.3 equals 0.3. So 0.1 K2 equals 0.6. So K2 is equal to 6. When we equate coefficients over here, we get 0.02 minus 0.01 K2 plus 0.02 K1 equals 0.02. So we have 0.02 minus 0.06 plus 0.02 K1 equals 0.02. So 0.02 K1 equals 0.06. And K1 is equal to 3. So finally, the controller gain matrix that we need is K is equal to 3, 6.